Okay, so about today, yep. Um, I'm going to talk about optimization with uncertainty. Okay, so um, let's first take a look at optimization problems without uncertainty. So if we have minimize x1 squared plus x2 squared and subject to a very simple one, x1 must be larger than 2, x2 must be larger than 1. A very simple problem. If I make a drawing of this, here is your x1, here is your x2, and here is x1 equals to 2, and here is x2 equals to 1. So you can easily draw the constraints. So if this is your G1, this is your G2. So we can say G1 equals to 2 minus x1 smaller than 0. G2 equals to 1 minus x2 smaller than 0. So this is the boundary of G2 equals to 0. This is the boundary of G1 equals to 0, right? And sometimes we would like to draw something like this, like a wall. So when I try to plot out the contour of our objective function, you can tell from the top view of this second order function, of course, it's like circles. So the iso surface, I mean the contour of this objective function would look like this. They are like circles. So this will be your f objective function, and along this direction, this is so-called the descent direction. So the direction of function value decreasing. And from here, you can easily tell, of course, this is our solution. X star will be 2, 1, because that's where we should be getting the lowest objective function value inside our feasible domain. Okay. However, what if we have something called uncertainty? What does uncertainty mean? Let's say x1 is one variable that may have uncertainty. So sometimes we say x1 looks like a distribution. Looks like a distribution. So sometimes we will say it's a normal distribution. And the mean value is x1. And the standard deviation could be, how about I say sigma 1. Okay. Sometimes people put a square here, sometimes not. So why does people sometimes, so what does those mean? N represent normal distribution. And over here, it's your mean value. And over here, it's your variance. So variance Sometimes people write VAR equals to sigma square. So what is sigma? Sigma is so-called the standard deviation. Okay. Okay. So when you describe your variable as a distribution, that means it's not always located at the mean value. Sometimes it changes. So in many cases, people will say, okay, x1 is actually x1 plus and minus sigma 1. So it's like there's tolerance. Okay. So what if we have a variable that has a tolerance, has uncertainty, has variance? Then it's very difficult for us to have a good design. Okay. So let me show you by MATLAB. Let me show you how uh, a uncertain variable look like. So let me turn on my MATLAB. Just want to double check if I have the whole screen. Yes, yes, yes. So maybe I change the size of my MATLAB and move to here. Okay. Oops. Okay, so in my MATLAB, let me write a very simple script. Come on. What happened? Okay, here you go. So if I let's say generate a number which is having mean value of 5 and the standard deviation equals to 1. And how about this? Let me create two variables. So let me say x1 and x2 are having the mean values of 5 and 6. And their standard deviation, let me call them S1 and S2, equals to, let's say, 1 and 2. How about that? Over here, you could certain. You could generate random numbers in certain distribution. Okay, so in MATLAB, if you use rand, representing random, actually it's a uniformly distributed random numbers. So there are some other kind of random number generator. So we are going to use this one, rand n. So rand n means you are generating normally distributed random variables. Okay, so MATLAB was able to uh, did some calculation and generate a bunch of random numbers that follows certain distribution. So let me just say number of points equals to let's say 1,000, 10 to the power of 3. Let's generate 1,000 points. And so capital X, x1 equals to rand n, so which means we're following normal distribution. Over here, you can just put number n here. But by default, when you generate normally distributed random numbers, it's gonna range from it's gonna having a mean value of 0 and the standard deviation of 1. Okay, so by default, the mean is 0 and standard deviation is 1. So this kind of normal distribution is so-called the standard normal distribution. Standard normal distribution. Okay. So I need to match all those points to my values. Okay. Oh, I couldn't define variables like this. Sorry. How about that? Just x and s. Yeah. Okay. So my x1 will be scaled by the value of the first standard deviation. So this equals to x1 multiply by multiplying the s bracket 1, the first standard deviation. And then it's going to be moved to the mean value, so small x1. Okay. And how about the x2? x2, similarly, capital X2 multiply the second standard deviation and translate to the second mean value. So I'm gonna do that. So that those are a bunch of random variables in the first coordinate and some random values in the second coordinate. So what if in my design I have those two variables and they both have these kind of variance? I'm going to plot out their coordinates and see how it look like. So let me just say plot all the random x1 and all the random x2, and I'm gonna just use some points and take a look. What did I recognize? Why? I didn't randomly generate x2, sorry. So I should do the same thing as well. Okay. So these are the points. So they are like a circular. Actually, they are not circular shape. Let me equalize the axes. They are distributed in a like an ellipse way. Because the standard deviation of x1 and x2 are different. The standard deviation of x1 is 1. So the horizontal width, the width will be narrower. And the standard deviation of the second one is 2. So the height of this whole thing will be taller. Okay. So now, sorry. So now you can tell if I randomly generate uncertain variables, they don't stay at the same point. They randomly distribute, right? Let's try to plot them in the same color. Okay, so if I plot them in the same color, it's like this. Let me try 100 points. I think 1,000 is too many, right? So this is like uh, 100 points. So people would like to figure out a way to um, they would like to draw a contour representing how much point that are inside this contour. So to draw that contour, let me figure out how I can show you that over here. So let me change to a circular distributed range. So this is more circular range of the uncertainty. So I will try to find a boundary that represent certain percent of the point, a circular range. So I'm not sure about the radius. So let me define some. I need to determine certain radius so that it represents certain amount of percentage. So let me. You need to calculate the distance from each point to the center. So the distance equals to each point minus the mean value, which is x, and then you need to do square and then sum together. When you sum, you are summing along, I think, this direction. Let me see if I'm right. You cannot do that. Can I do this? Oh, they don't allow me to do that. So I need to write a for loop. For I equals to 1 to number of points, the distance, the ith distance equals to the vector of I know because I know why, because this should be like this, vertical vectors. I think once I do that, I should be able to do this. Let me do it again. So how come less points? Okay. Anyway, yes. So the distance. No, this is not what I'm looking for. Summing along the second direction. Yeah. Okay. So what I did was I have a bunch of coordinates. They are like this. Where's this? Okay. I have a bunch of coordinates. Uh, I call them capital X1 and capital X2, right? So it's actually they are a bunch of random numbers and totally n by 1. I have a bunch of n by 1 um, uh, variables. And when I say capital X1 and capital X2 minus X1 and X2, S1 and X2 is a 2 by 1 vector. 1 by 2. A 1 by 2 vector. And this whole thing is a n by 2 vector. How can these two vectors do plus and minus together? In MATLAB, you can. So this is n by 2. So when MATLAB realize you are doing summation or subtraction between two matrices, they are not in the same size. They will. MATLAB is very smart. MATLAB will do this element operation for you. So what will happen is you will get x1 the first one, x2 x1 the first one minus small x1, x1 the second one minus x1, da da da, x1 the last one minus x1. And over here you will have x2 the first one minus x2, and da da da, and so on. So MATLAB will distribute all those minus x1 to each component. That's why my code could be short. You don't want your code to be long, right? So once you do that, what I did was I later on use a operation of dot and head and two. So basically, it's a dot operation. It's basically operating square operation to every component. So at the end, every component will have a square. Every one of them has a square. Okay? So this does that. Okay? So once every component is squared, then I sum them together. So in MATLAB, when you say sum of a matrix, you can either say 1 or 2 over here. So when you say 1 or 2, it's representing you are summing along the first dimension or the second dimension. So based on what I did, when I say 2, I'm summing along the second direction. So when I sum second direction, it's summing, oh, I should sum 1 so that I only have two numbers. So I should sum vertically. So the end, no, I should sum horizontally. So but 2 is right. 2 is right. I'm summing horizontally. So if we go back to my iPad, it's like you're operating this. You do a bracket here, and you're summing horizontally. So this horizontal part will be summed together. This horizontal part being summed together. So at the end, I should have n results. So at the end, I should have n results. Here, 10,000 by 1 of those are sums. And when I finish those summing, I should take a square root. So over here, I just need to say square root. And MATLAB could do square root on each one of them. So I still have 10,000 results. And if you take a look, basically they are the distance from each random point to the mean point. So that calculation can be done in one line. Okay? So that your code is short. So now I have the distance. I want to sort them. I want to sort. So let me just do, say, sort x. S represents sort, and I need the ID of it. ID represent the index after sorting, and I'm gonna do sort distance. Okay, so once I have that, XS will be, actually I should say distance sort. I'm sorting the distance. So distance sort, this is sorting from small to the largest, from the smallest to largest. Yeah, let me sort. This is small to large. Okay, large. Now I need to have a target um, target percentage. target or target, yeah, let me say percentage. So let me say 0.95. So what does that mean? I want to draw a circle that covers 95% of points. That's what I want. Okay, and then, but I don't know how large the radius is gonna be. So this is what I'm going to do. I because I sort them already, so I can just quickly count which is the one that should be included and which is the one should not. And since all the distance from the point to the center is being sorted, so I just need to check what's the distance of the point that is right on the 95% mark, right? So totally I have right now, 10 to the power of, oh, I did 4. Okay, that's fine. So if I have 10 to the power of 4 points, what's the one point that is standing on the 95%? Then the index of it will be, so let me call the target index will be n times my percentage. Okay, so if I have 10 to the power of 4 multiplied by 0.95, then I have 9500th point. So the 9500th point will be having this target radius, right? This, so I just need to check at this target index, what's the distance from itself to the center. So the result is, so my target radius will equals to the distance sorted and the ID, the target ID 1. So supposedly that will be my target radius. So let me draw a circle with that radius. So how to draw a circle in MATLAB? Let's write a, you can say, so directly plot. And how about, I want to make a short one. So it's gonna be target radius multiply cosine. So let me draw from 0 to 2 pi, right? And my sampling will be, let's say, 2 pi over 100 of them. Okay. So, but I need to sum the radius. So the radius, the center point is x1, and my y coordinate will be sine. And I want to link them by a line, a red line. Let's see. Oh, I didn't hold on. Something was wrong. Here should be x2. Okay. Let me make it thicker. Line width. So this circle is covering 95% of points. Is it true? Let's try to cover 99 point something percent. So 99, how many nines? 4 nines. So maybe only one point is outside. Here's one. Here, this one is outside, right? So I have 10,000 of it, and I want to cover 9999 of them. So only this one is outside, right? So that means my coding was correct in one shot. I'm happy about myself. So let's see if I have a greater amount of points. Then this is like how many? A million points. A million points. Okay, so it's like whatever you want to discuss about normally distributed random variables probably could be discussed by regarding to this red circle. So in the field of optimization with uncertainty, sometimes people are playing with this red circle. So as long as this circle is not violating my constraint, that means I know this percentage of points will not violate. This is how they try to control the randomness of points. Okay, and let me explain to you more about why this is important. Because if we go back to the previous problem, this one, what if my design point has uncertainty? What if my points has the uncertainty? What's gonna happen is that your design point inside the space, this is a point inside the space, actually is having certain distributions. Okay, and if we did what I showed you earlier, we should be able to draw some circles, and maybe this circle is like a 98% of its possible position, probable position, right? So maybe there are some points outside, but only like 2% of points is outside. And if this uncertainty is always there, then when we get our optimal solution right here, we should have the same uncertainty near the optimal. So we can actually also draw this contour to represent how wide the uncertainty is. And if you look at this is a disaster. Why is it a disaster? If we zoom in, if this is the 98% contour of my uncertain variable, x1 and x2, okay? From here, you can tell this area violates G1, right? How about the other area? This area violates G2. So can anyone tell me what's the failure rate? Failure rate. 75%. So you only have a 25% of success rate. Very bad. So how do we get a 99% success rate or 98% success rate? How do we get it? So in this field, if we have, this is my G1 equals to 0. This is my G2 equals to 0. And over here, I don't want to go to the left side. I don't want to go to the lower side. And if I can find a design that is having this percentage contour having tangent at the limit of the constraint, then let's say this is 98% contour of my x1 and x2. So I can definitely make sure the probability of function g1 using x1 and x2 plugging in, on the right hand side is g1 smaller than 0, on the left hand side is g1 larger than 0. So I can say, if I want to say the success rate, so the success rate should be smaller than or equal to 0. I can say the success rate definitely is larger than 98% in this case, right? Because 98% of the points definitely is on the right hand side of G1. So I'm very sure the probability of Gx smaller than 0 definitely is greater than 98%. So this is the event of G1 satisfying G1, right? And this whole thing basically is your success rate, right? And over here, basically, you can make sure the success rate is larger than 98%. Okay? And similarly, of course, we can formulate the second equation. So in the field of optimization with uncertainty, people would like to reformulate the problem. Originally, we have minimizing x1 squared plus x2 squared subject to gx1 equals to what? 2 minus, or we can just forget about that example. We can just use some general formulation. People originally would like to handle something like this, subject to some g function, x1 and x2, must be smaller than 0. But when they know x1 is a normal distribution like this, and x2 is a normal distribution like this, then they need to reformulate the problem like this. Over here, when you talk about x1 and x2, basically is the mean of capital X1. And here become the mean of capital X2. It's blocking. Okay. So you are still trying to control the mean value of the uncertainty. You don't control anything else. You only control the mean. And if the uncertainty level is the same, the only difference is you can try to change the value of your mean value. So in reality, it's like for, let's say you have a mechanical design and there's a dimension which is 10 centimeter. So let's say your standard deviation is 0.1. So it's like you want to design the dimension within the range of 10 plus and minus 0.1. So if one day the cat drawing change to 8, maybe the level of uncertainty remain the same, but the mean changes. So you change to 8 plus and minus 0.1. Okay, so it's quite common that we change the mean value, but about the uncertain level, usually we don't change much, right? For example, uh, if certain dimension is made by certain manufacturing process, usually the tolerance range doesn't change much. Okay, so that's why usually at the beginning of uh, entry level of doing optimization with uncertainty, we usually handle uh, a fixed variation on each variable. Even with that, it's already more complex than what you learned in the past. Okay, so this is about the objective function. How about the constraint? So when we know the variables are having uncertainties, the constraint formulation needs to be changed. Let me actually move the whole thing to here. I think I will have more space. Okay, so the constraint, just like I showed you earlier, we would like to handle the probability. So P represents probability. Probability of what? You can either control the probability of success rate, or you can handle the failure rate. But in our field, usually we talk about the failure rate. So so what would be this is the success condition, right? So what would be the fail condition? The fail condition would be g of x1 and x2 greater than 0. So when we talk about the failure rate, here we put capital X1, capital X2 greater than 0. So this is basically the failure rate. This is so-called the failure rate. Should be smaller than certain limit. So usually we call here allowable failure rate. Okay? So sometimes we call this PF. So this PF could be very small or could be large. It depends on your design. Okay, so when we talk about uncertainty, there are several new things. The first thing is your variable become randomly distributed. So sometimes we call those randomly distributed variables. And it could be distributed in many different ways. So sometimes we will talk about what's the shape of the distribution. So it's like a distribution type become a factor to these kind of problems. And also, usually, our variables are the mean of your random variables. So that would be that those remain our variables. And lastly, most importantly, your constraint needs to be changed. We start to talk about failure rate, and the failure rate needs to be smaller than certain level. So when we have a problem like this, how do we handle it? Okay, if you look at the MATLAB, and if I show you the radius, let's take a note of the radius. So excuse me. Let me write a for loop and then plot out several different combinations of target percentage and also their resultant radius. So let me write a for loop here. So for target radius equals to, let me set a range, like a 90%, 95%, 99%. Actually, there's a, yeah, 99%, and also another one, 99.87%. It's a very unique number. I will explain later. And I think that would be enough. So for those, we're going to do the same thing. And we will get multiple numbers of radius, and they will be plotted out. And I'm gonna also display the result. So display. So when we have this PF, allowable failure rate, when we have this, so basically when I talk about this target percentage, is actually the allowable failure rate. Okay, so over here, I'm going to plot out the radius of that circle. So the radius should be target R. And take a look. Okay, so you see a bunch of circles in different sizes, and maybe I need more. Hold on. Yeah, it's 99.87. How come it's quite different from what I think? It's quite different from what I think. I know why. So I should say maybe, never mind. I was trying to show you a magic number, but I failed. It's fine. So maybe we just focus on three different kinds, and then maybe just a million points. Okay. So from here you can tell when we have like 10% of point outside, the radius is 2.1. And when we have 95%, the radius become larger. and larger. Okay, so this is in the case where we have standard deviation of 1. So the radius, this is like 3 times of your radius. So have you heard of 3 sigma? So when people talk about 3 sigma, it's very related to what we are seeing here. So this red, the largest one, largest one, when we have 99% of points inside, our radius of this red circle is close to 3 times of your sigma. So it's like this range is about 3 times of your sigma. So when people say 3 sigma or 6 sigma, they are actually talking about this circle. And when they, so 3 sigma basically is the range within certain percentage. Okay. If we can kind of convert the percentage into this radius value, maybe we can directly make an offset of the constraint by this value. So imagine we have the previous problem where we have constraints like this. This is my G1. This is my G2. And if I know there is this circle representing probability I should say probability of so let's say this is R. Probability of those points minus the mean value and calculating the distance. And the distance is smaller than R. And this percentage is basically your target probability. Sorry, it's blocking again. So let's say I have a circle with radius of R, and it's representing how much your X is having a distance from your mean. This is your mean. This is your random point. And the distance between them is within this radius. So the probability of those equals to your desired probability. So let's say you have a circle like that. Then we can probably call this PF circle, just for short. So this circle is representing PF. Okay, and if we know this exact number of radius, then why don't we just make an offset of R and make an offset of R? Let's do that. And let's ask this point to be moved to this position so that this PF circle will be tangent to the original constraint. So when you do that, you can control your failure rate. This is how you can control the failure rate. And this, of course, is easy if you can just do the offset. It's easy. But this is only easy when it's in linear problems. So let me show you two cases. This will become very difficult. So one case is that when we have nonlinear constraint. So let's say I have a constraint like this, another constraint like this. Okay. So if originally this is my design point, and what if and maybe your f descent direction is going that way, so supposedly this will be your optimal solution, right? Because it's pushing the descent direction of f is pushing your point and move your point to the intersection between these two constraints. However, if my design point has a so-called PF circle representing the range of this uncertainty, then the goal at the end is to move the point to here. You cannot move further. Otherwise, the failure rate increases. Okay? So how could you move to this position without penetrating through the wall? You have to do what I mentioned about. You need to do that offset. So when you offset the constraint, it's like in every position, the direction of the offset is different because it's nonlinear. So the most difficult thing is how do you get that offset constraint? And sometimes we call this constraint probabilistic constraint. So in the past few years, many researchers have been working on how to formulate this probabilistic constraint. It's not easy. Okay, so that's one tricky part about this problem. When the constraint is nonlinear, it's not easy. If it's linear, it's very easy to shift one line to another position just by shifting the coordinate. But for nonlinear one, it's very difficult. So what would be the second problem? So non-normal type of your distribution will make the problem much harder as well. So let me show you why. Let's say I still have linear constraints. So those are linear constraints. Okay? And I have my random points. But what if my variable uh, varies in a new distribution way? So maybe your uncertainty looks like this. Then there's no something called radius because the distance to here, distance to here, distance to here, every distance from your center to the edge. So maybe this is the 98% of the uncertainty. But the distance from the center to the edges are different. Then it's very difficult. So let me show you some examples. Okay, so in this case, you can tell those variables are distributed in a very weird way. And the two red lines are the original constraints. And when I make a movement, the black lines are the probabilistic constraints. And originally, the points, the mean value of the points is right at the intersection of the two red lines. But later on, when I iterate, we figure, okay, I need to shift the red line to the black ones. So the distribution moves, and you can control how much points is outside of the red. Okay, let me show you another example. This is another one. So the difficulty of this field is that we are handling design points with many different kinds of uncertainty. Even when the problem is linear, it's quite difficult. This is another one. This is usually a distribution like this doesn't exist in the world. This is a combination of uniform distribution and normal distribution. So this case is just to show some methodology works. Okay. So from the animation, you should be able to learn more about what is design, uh, what is optimization with uncertainty. Oh, I need to. Okay. So from here, if I would like to have a safe design, I wish this distribution will move to here, like this. Then, when I control the mean point, I need to calculate how much offset should be, right? And what if I have a very nonlinear problem with a random distribution? So together, if I have a distribution like this, and if I have a constraint like this, some arbitrary drawing. So the goal is I would like to copy this and paste it and move it to maybe somewhere here. So look how much I should offset. I should offset this amount over here, and I should offset this larger amount here. See, the amount of offset will be very different. That's the difficult part of this kind of problems. Okay, so it's impossible for me to introduce everything about this today, but at least I can show you there's a kind of problem like this in the world, and there are a bunch of researchers are working on this. So what can you do today? Let's start with the most simple one, and I can teach you some fundamental about this, and maybe you could later on use it in your research. So to show you that, I would like to get some notes. Not this one. So should be this one. let me try to start from scratch. So, okay, the idea is that I would like to evaluate probability of my constraint function and with my variable plugging in, the uncertain variable, and larger than 0, and this should be smaller than my failure probability, the allowable failure probability. So the problem is, how do you evaluate this? Because whenever you, during the iteration, when you have your design values, you need to plug in into your function and then check what's the current value of your function. And the optimizer will determine what would be your new design point based on those evaluations. So the key is you need to evaluate this. Need to evaluate this at some design point. So when we say some design point, that means at some design point, mu means mean value, mu of x, or like what we used earlier, use a small case of x, and maybe bracket k. So this is like mean of x at kth iteration. So at some iteration, you have a mean value of your x, and you would like to know what's the probability of this event, okay? And like what we did earlier, we can use a for loop. If I have 1 million points, I can plug into this function 10 million points and just do some sorting to check, okay, how many percent of point is satisfying, how many percent of point is not. So I get this number, P probability. So the easiest way is to plug in this function n times. So n means number of random points. Okay, so you can plug in into this function. Oh, I made a mistake. You can plug in and check how many percent satisfy this function. So once you check, you basically get this value. Okay, so in computer, it seems like it's easy. But what if this is reality? What if this is your thesis and you tell your boss that you would like to work on optimization with uncertainty, and you basically will use a machine tool to cut certain piece, and you are going to evaluate your success rate. And let's say the dimension of the workpiece is 10, and you are going to repeat this cutting 10,000 times so that you can evaluate if these 10,000 pieces satisfy certain constraint, like weight or strength or anything. G could be anything. So that means you need to operate your experiment 10,000 times and also evaluate what you are interested 10,000 times just to get one evaluation in optimization. And then your optimizer will say, oh, okay, good job. Now your probability is 85%. Based on this current probability, I suggest you to move your design point to somewhere else. Please do 10,000 times again. It will be like that if you do it like this. Yes. And let's say in your previous homework, how many iterations you need for one case? Maybe like 5 or 10. Let's say 5. And each time you do this 10,000 times, you need to do 50,000 times. Before you finish, your boss is bankrupt, right? So it's impossible for you to do this in reality. That's why people start to deal with so-called the radius, because radius is one number. Probability needs sampling. Okay, so can we convert this whole thing into what we mentioned about the radius? Okay, so if you would like to learn about this, you need to be aware when you have a bunch of uncertain variables and you plug in into this g function, what you will get is like a bunch of values. Because this is randomly distributed, even your function is a very consistent system. What you will get at the end will be randomly distributed. Right? Because you have 10,000 different numbers. You plugging into the same function. You should generate 10,000 different function values. So over here, this is itself is a uncertain, the g is an uncertain value. Okay? So let me figure out a way to help you to learn how to convert this into maybe I show you in a graphical way. So now let me try. Okay, let's say here is your g value. Okay, and here is g value equals to 0. And based on what you did, maybe over here we are looking for larger than, right? Larger than. Okay, so maybe here. Let's say this is a g value if you use the mean value of x to plug in. Okay, and because you have 10,000 points plugging in into the same function, you should have a distribution of those. So what's gonna happen is that this will be the normal distribution of your g function. And when you plug in all the points into your g, okay, this is how the distribution should look like. Okay, and what's my what in this kind of plot? What's my y-axis? This is so-called the probability density. Okay, and sometimes people denote this as p. Okay, and when you have a drawing like this, people usually call this function probability density function. So this is called so-called a PDF. So in statistics, PDF is not PDF. PDF is probability density function. Okay, and we are looking for this randomly distributed G greater than 0. So what does that mean? That means you are drawing a line here. You are trying to calculate the area. So this is basically the probability of this G greater than 0, the area of it. And from here you can tell if I have a PDF function, I want to calculate the area within certain range, what do? Integral, right? So if you want try to do that, you can do an integral. In this case, you're doing integral from 0 to infinity, and I need to denote my PDF. So let's say this PDF is called usually small case of f, and here I can say small case of g here. Just let me just call this f, small f. So basically I'm doing an integral of small f. And here in this case, basically it's a difference in g. Okay, basically an integral. Okay, but like I said earlier, if in reality it's difficult for integral. The integral in reality is to do things multiple times and then count, right? So it's impossible to do this. But at least you understand. Okay, this is integral, and some people would like to call this um, a function like this, and they usually call this um, g equals to 0. So when they use this notation, they are talking about CDF. So what is CDF? CDF is so-called the cumulative distribution function. Okay, so when they start to uh, the sum up the area underneath certain range in this PDF function, whatever they are getting is called the CDF, the cumulative distribution function. But be careful, whenever you use this CDF, you need to be very careful because you need to check whether it's calculating the left-hand side of the integral or right-hand side of the integral, or maybe even a portion, maybe an integral from A to B. So that whenever people talk about this CDF, they also need to carefully check what's the range of this integral. Very important. Okay. I don't maybe change another color. The range. Here's the range, right? Okay. I realize if I use this format here, it will be difficult for you. So, but at least I introduced the concept of PDF and CDF. So in order to go further, I need to simplify this problem even more. So let's talk about an even easier problem where I would like to say a g function equals to, let's say, 2 minus x must be smaller than 0. A very simple one. So this is basically x must not be larger than 2. And let's define our capital X, basically the uncertain one, is having a distribution, a normal distribution, and the mean value can be changed, but the standard deviation is 1. Okay? And let's say I'm looking for probability of failure of, there's a magic number, 0.13%. And that's basically 3 sigma. Okay? Uh, we'll see later on. Okay. So how can we, so what would be this? What would be my mean value of x so that my failure rate is exactly 0.13% and exactly matching 3 sigma design? So how do we, so what will be my mean so that it will satisfy those? Okay. So in this case, we could make a drawing again. In this case, I'm drawing in the coordinate of x. So over here, this is where x equals to 2. So this is where my g function equals to 0. So let me draw a boundary, okay? And I can show you several cases. Actually, this is what we're looking for. Okay. If my x equals to 5, and this is the range of 1 sigma, 2 sigma, and 3 sigma. When we have a case like this, and I can tell you this area is exactly 0.13%. So let's check this design. Do we have most of the points on the right hand side of the limit? Yes, right? We have more than 99%. So over here, this is like 99.87% of your x. 99.87% of your x, that is on the right hand side of the limit. So this is sometimes called the limit state. So 99.87% of your x is on the right hand side, which is safe. So this on the left hand side only 0.13%. And this is basically your failure rate. Only 0.13% that violates the constraint. So we wish we could find this solution. We need a mathematical way to figure out, oh, okay, x should be 5. So how do we do that? Again, this is my PDF. So in this case, I'm using small case of f, and then I put a capital X right here. So this is like the f function regarding to the random x. So this PDF varies with respect to small x because the horizontal coordinate is x, right? And what's my vertical coordinate? It's p, the probability density function. Okay, so in this case, when I try to calculate the failure area or the failure probability, basically I'm trying to calculate this. So here is so-called the failure rate. Will equals to an integral from negative infinity to some position. So over here, let me call this position xa. Okay, xa. And my PDF x and then dx. Should I use xa? Let me think about it. Ah, yes. This position of xa is very important. Okay. Uh, so when people try to analyze this, they would like to convert this whole thing into a different coordinate. So this conversion is very important. Let me show you here. So need to convert to another coordinate, so-called the standard normal space, a different space. So how do we do this conversion? Whatever that is x now change to a symbol called u. So u is the standard normal variable. So how do you compute u? U will be whatever your x is minus the mean value of your distribution divided by the standard deviation of your x. Okay, so this is how you can convert your original space, which is x, and then convert to u. This is the relationship between x and u. Okay, so let's try to do that. And then in our case, we actually have x minus, what's my mean? Mean value is 5. What is my standard deviation, which is 1? So we are actually just doing a horizontal shifting from the origin to this new position, x equals to 5. So let's try that. My problem is here. Copy, paste. And I want to do this conversion. Okay, so let's try this on the constraint first. So my G in the U space, in this standard normal space, becomes 2 minus. So from here you can tell x equals to U plus 5, right? So just plug in. So here this becomes U plus 5 and smaller than 0. So this is becoming U greater than negative 5, right? So this is becoming U greater than negative 3, sorry. So when I convert, originally, this is x equal to 0. This was x equals to 2. This was x equals to 5. And originally, I have a shape like this. And here is I call this xa, and this is my limit state, basically where my x equals to 0. And I was trying to calculate the area of here. Now I convert this whole thing into a different space. But in this different space, everything was converted to U. So here is the U space. Here is where U equals to 0. This is where U equals to negative 3. And because we did the conversion, I think I better call this UA. Basically the same point, but different coordinate. And also, this line is still where my constraint function equals to 0. This is just a linear conversion, right? So in this case, we can tell this value is actually my UA, is it? Yes. So in this case, this is my UA. Okay. So originally this is called the small f of capital S X. So this is my random distribution capital X. Oh. But in the U space, we call this capital U, and we call this f of capital U. Okay. So this is the original space, and this is the standard normal space. So over here, what we try to do right now becomes what is the probability of. Oh, I need to plug in. Sorry. So originally we would like to evaluate probability of G capital X greater than 0. This is what we want to evaluate. Now when we convert, since we have this equation, so the conversion will be capital U equals to capital X minus sigma minus mu over sigma. Okay, so small k's represent a point. Capital K's represent the whole distribution, and the whole distribution follows the exactly same transformation. So now this was 2 minus capital X smaller than 0, right? Because when we plug in the whole distribution in there, I want to evaluate what's the probability of this event. Sorry, here. Here should be larger than. We want to evaluate this. So after conversion, this becomes basically capital U greater than -3. Basically like this. Okay. Um, the good thing about standard normal distribution is that uh, all the probabilities has been calculated. So let me show you. If you Google for it, you can easily find it. So normal distribution table. Sometimes it's called the Z-tab table. Maybe this one. Okay. Let me download. Save image. I should download the original file. So I should say save link as. No, not the link. So maybe just go there. Okay, this is very clear. When you have this so-called Z table, actually it's a standard normal. See, standard normal probability, and it's telling you the distribution is following the standard normal distribution. The mean is 0, and the standard deviation is 1. And it's saying, okay, the area on the left-hand side of Z, basically what I use XA, but over here they use Z. So they already calculated the integral. The area on the left-hand side of z equals to certain number, and the numbers are listed in the table already. So in our case, let's go back. In our case, we're looking for -3. So we just need to say go there, go to the table and looking for -3, right? So -3. -3 is right here, exactly here. So this in this table, -3.0, this is another point. So if you're looking for -3.01, then you need to look at the second row, second column here. But for us, we are looking for -3.00. So this is actually the value here. And did you remember I told you the area is 0.13%? Because this is what we always work on in a paper. So we memorize the number. So here, from here you can tell, oh yes, you're right. If my design is like this, if I chose my x to be located at 5, then this tail will be over the limit by a certain percent, but I don't know how much. I could convert my original problem into this standard normal space. When I do that, I need to check what's the value at the tail over here at the limit state. And I realize the u is -3. Then I can go back and check my z table to tell what's the percentage right here. Okay, so that's how you could do. You can evaluate your uncertainty. Let me show you another case. What if we have a different position? So my problem was like this, and I would like to evaluate a variable like this. Maybe my design is 6, and my standard deviation is 1.5. So I would like to know what is the probability of failure. Okay, so how do we do that? So first thing is that we can do a conversion to the U space. So over here, I need to minus the mean value divided by the standard deviation. So over here, all my capital X becomes 6 plus 1.5 U. Okay, so I would, so over here, what we would like to evaluate actually was 2 capital X smaller than 0. We want to evaluate this. And this basically could be converted to here. Probability of 2 minus 6 plus 1.5 capital U smaller than 0. And we can rearrange this whole thing. So I can have, this is a -4, so 4 on the right hand side, negative 1.5 U here. So this will be probability of U larger than 4 over 1.5 is negative 2.67. Okay, right? So you're actually evaluating this. Now we can go back to the z table again. You are checking the area greater than it's on the right hand side. Why is it on the right hand side? Because I was checking I made a mistake, sorry. This guy I made a mistake. Here should be greater than. because we are checking the failure rate. So here should be greater than. So here should be greater than and smaller than. This is greater than, this is smaller than. So we are looking at something like this. This is 0, this is my U space, my standard deviation is 1. Sorry. I made a mistake about the sign. So here was wrong, okay? We were talking about the failure rate, right? So I made a mistake. This is the safe design. So when we convert down to here, we are talking about a design in the U space, and here is a point of negative 2.67. So basically, we want to know what's the area of this, okay? So the area of that can be evaluated by the z-table. So z-table negative 2.6 and 7 here. So it tells you it's 0.38%. So this is 0.38%. Okay, so then you can evaluate your probability. If you can do that, you can then operate optimization. So how do you operate optimization? Take fmin_con as an example. You have fmin_con. This is in MATLAB. You will throw in your initial design. And inside fmin_con, you need to write two codes. One is your function, objective function, and then the other one is your constraint, right? So inside your constraint, you can write certain codes to evaluate probability. So every time you assign a design point to fmin_con, it will just operate like what fmin_con did in the past. But whenever it's trying to evaluate the constraint, you need to help MATLAB to compute the failure rate or success rate. So what you need to work on will be how you formulate the probabilistic constraint inside this MATLAB function. Okay, and I can show you what would be the commands for calculating the z-table in MATLAB. So if you would like to get the z-value in MATLAB, norm CDF -3. So norm CDF means normal distribution CDF. -3 is the UA. Plug in, it tells you the probability on the left hand side of the U space. So what you could do in MATLAB is that when you try to evaluate, if you already convert something to the U space, this is U equals to 0, and here is some UA value. So the area over here basically is integral from -infinity to UA, and this is basically a CDF in the U space. CDF in the U space, and then the coordinate, this is du. So basically this is, we sometimes write this. So this is called a CDF of the standard normal distribution. So in MATLAB, you can directly say norm CDF and put in the value of UA. That's that. MATLAB will automatically compute the integral and then tell you the number. Any UA, it will tell you. But this is only 1D. How about 2D? If you want to learn 2D, you need to join my lab. We're too hard. Maybe I show you something. Just show. Because to explain that is taking too much time. Let me see if I could. See, we are doing integrals. So for multi-dimensional, the failure rate, the probability of failure in multi-dimensional is this huge, crazy integral with multiple dimensions. It's impossible to solve, but people convert it into this. See, this is a CDF of some value. So in my lecture, I call this UA, but in this document we call beta. Okay, and oh yeah, eventually you get something like this. So this is like my hand drawing maybe 20 years ago or 10 years ago. I forget. Maybe 10. 2000 and yeah, 10 years ago. Yeah, my hand drawing. Maybe I show you something else. Maybe this one. Okay, so over here, this is a linear design problem, and from here you can already see the contour of the objective function. Blue color represent lower function value. So if I have a design point right there at the center, the optimal is right here, because that's where you have the lowest function value inside this triangular domain. This is if we have like a regular, we call the deterministic formulation. However, if we have uncertainty, and if we have two kinds of uncertainty, one is 98% and the other one is a magic number, 99.87%. And if we look at the optimal design, we have failure. We have 50% of G1 failure. We have 50% of G3 failure. So very, very bad. So in total, the failure rate is more than 90. Okay? So in reality, what we do is we apply something called safety factor. The safety factor is usually applied to one variable. But only a few people knows how to handle multi-variable. Researchers like us, only we do it. And there are some softwares, they already provide optimal design with uncertainty. Basically, those softwares were developed by researchers like me. So they are maybe several professors, more than 10 professors, they already sold their software package to some company. So that's why some of you probably can find a software to handle something like this. Yeah. But at least you need to know what's going on inside, right? Today is the day that I tell you what's going on. So these offset basically are the offset that represent different levels of safety, different safety level. So like the first constraint, we would like to have 99.87 success rate. Second one the same, but the third one, maybe we like 98% only. So with this new offset, from here you can tell the smaller ellipse is contacting the G3 and the bigger ellipse is contacting the G1. So they will satisfy the safety level of each constraint. So from here you can tell the G1 failure is controlled as 0.13% and the G3 failure is controlled as 2%. So the safety level for each constraint can be different. So different so-called PF contour can have different sizes because it depends on what PF you are using. Okay? So this is what I did long time ago. Basically, see? Transformation to standard normal distribution. Exact same thing. But over here, this is the thing that was not covered today. It takes maybe 6 more hours to explain. I don't know. Couple more hours to explain. So I'm not going to cover those. But basically, you could see how you could see how it iterates. So like here, initially the optimal goes to here, then the probabilistic constraint updates. So your design point moves little by little until you move to the optimal solution. This was talking about some issues about the old method, and this is the new method. Formulations and examples. So maybe I show you something else. This one. Oh, this one. I hope it's still there. Oh, okay. Huh. So in the multi-dimensional case, we need to find it's like a tangent point, perpendicular point, or we call the closest point to your design. And that searching is a sub-problem that solves this, like a distance minimization problem. Can anyone imagine how I draw this? Take a guess. What software? No? I'll give you a hint. When I was a TA in Rutgers, I teach CAD drawing, Pro-E. It was drawn by Pro-E. So how come Pro-E can do this animation? I think I put two spring on the left hand side and the right hand side of the green circle, and then I think I pull the circle, the ball on one side because of the spring force. It will do this until it stops. So that animation helps me to show the procedure of searching. So because I was TA of Pro E, so I was able to spend time to do this. So when I made this and present this in an international conference, many people came up to me and asked me how I did it. So that's how I draw attention to the audience. So there's another problem, which is a different approach. I also use Pro E to do it. So in this one, it's a different way of searching, but it's searching around a circular area. The circular area basically is the PF circle that we mentioned. But in this approach, we don't search on the limit state. We search near the design point. Okay, so uh, I would like to use fancy animations to help people understand. What I remember, there's another one. No, no more. Let me see. I remember there's a quite fancy one. Where is it? This one? Here. No, it doesn't. So in the past, because during the time when you create videos, I think it's mostly in the format of maybe MPEG 2. I think MPEG 2. Do you know about MPEG 2? Before MPEG 3. So MP3 is MPEG 3. So MPEG 2 was the video format long time ago. And later on they create MPEG 3, basically the audio format. And then they create MPEG 4. So you only heard of MPEG 4. Actually, there's MPEG 1. So I think those many of my videos was made in probably we call the codec, basically the data format for videos that we call codec. So I think this was made in the codec of MPEG 4, and or it was made in WMV, Windows Media Video, which is very bad. I don't like it. But at the time, if you don't insert a WMV video to PowerPoint, it doesn't play. So many times we need to create a videos in certain format so our PowerPoint can view. But nowadays, maybe all the computers already ignore those old formats. So many of those old videos doesn't show. I'm not so sad about this. And I don't even know where I put those. It was like, see, 2010, 10 years ago. So anyway, I had this. Uh, in the previous slide, everything is like in the top view. I made the animation of spinning the coordinate and then view in the angular, view the whole thing in this angular view. So and what else? Okay, so this was the animation that I explained the difference between two methods. The first method was trying to find the closest point on the limit state, and the second method was the way to find the closest point that on this PF circle, the red circle, but it's facing the same direction. Yeah. So anyway, that was my PhD work. So if you would like to study for PhD, you should create nice presentations like me, right? Okay, I think that's pretty much I want to introduce today. That would be that. This is already a lot. Uh, so if you in the future, when you handle a design optimization problem and you realize in your problem there's some uncertainty somewhere, but you forget about how to do it. Don't forget about me. Just send me an email. Maybe I can give you some help. Okay. You, I'm probably the only person who will teach you something about optimization with uncertainty in your life. Because in Taiwan, maybe there are only less than 10 people working on this, or maybe less than five. At least when I go to the most important conference about this, I'm the only person. So I can say I'm the guy I'm the only one who is working on this. I know there are some professors who are also working on this, but they are in civil engineering. Because in civil engineering, they are working on concrete or different all kinds of materials. The material properties are always uncertain. That's why this kind of design optimization is very important for them. And also, whatever they are building, it's about human life. So they usually need to evaluate what's the safety level of certain things. So for us, we also need to work on safety level, but usually in the course of mechanical design, we sometimes talk about failure of materials or fatigue. And usually in the textbook, they just increase the level of your strength, or they change the level of your strength so that your design range becomes smaller. Okay, if you think about this, what's happening in the traditional mechanical design is like this. Traditionally, uh, for most mechanical engineering designers, uh, they have a strength, and they have the limit, right? So maybe when or I should say differently. Let me say this is the yielding strength, and this is like the stress of your design, right? So usually, what's happening is that you your design has uncertainty, so there will be a certain range of uh, certain probability of your design failing. So this is probability of the stress over your strength, right? And you want this to be low. So if you design this way, your stress must be smaller than your strength. Then one possible design is under constraint. This become a possible design when the stress equals to your strength. This become one possible design. But this is not good because when you use this design, the failure rate is 50. 50% is outside. So what's happening is they design a different way. They say stress must be smaller than your strength over a safety factor. Usually it's like that. So sometimes it's like for example, half of the strength. So it's like they shrink the limit state to somewhere maybe here. Maybe this is half of the yielding strength. So you wish your stress to be smaller than half of the yielding. So when you do this reduction, it's basically the same thing like what we did today. Today we did an offset. And when you define the factor of safety, it's like you're defining how much you do the shifting. But usually in the most traditional way is that we give a certain number, like a 2 or 2.5 or 3. But all the lecturers about this field, they will say, when you go to the company, they will tell you what's the safety factor. So you can tell that this factor is really problem dependent. Why is that? Because most of the mechanical engineering and designers doesn't know about statistics. So they just keep on trying this factor until they feel like, okay, I think this is fine. If they make it too large, the design is too safe, the company is losing money because your design is too strong or the performance is too weak. And if the number is too small, that means it's not safe enough. So a lot of failure. So if you are able to use statistics to evaluate what's the proper offset for the design, you should be able to control the failure rate. So like nowadays, we don't want the design to be too safe. We want the design to fail after the warranty. Right after the warranty fail. Yes. So that's why our cell phone breaks in 2 years because the warranty is in 2 years. They are already doing it. They are doing it. Don't trust me. Like in Taiwan, we have like a rice cooker, 大同 rice cooker. In the past, it doesn't break in 10 years. Nowadays, it breaks in 2 years because they finally use statistics, right? So that's actually there are already people working on this, but in school we don't focus enough on this kind of stuff. Only civil engineering do this. So if in the future you really would like to know about this, the field is called system reliability. Okay, and what I showed you earlier, the fancy stuff, the kind of optimization is called reliability based design optimization. So-called the RBDO. Okay, so if you memorize those words when you need it, Google for it or Google my name, right? Okay, so that's it for today. I will see you 2 weeks from now. Hopefully you finish your project. Okay, and during these 2 weeks, if you have any questions, please send me emails to. Please don't just come at the office hour because that's a fake office hour. My office time is too random, okay, too uncertain. So that's an uncertain office hour. Standard deviation is plus and minus 3 days. Okay, so send me email. I will try to, yeah, answer your questions.